All righty, on to completeness in section 2.5. All right, so we'll start by reviewing some ideas of completeness you've been exposed to in the past, see how there's shortcomings to that in the current setting, and deal with those shortcomings in a way consistent with your past experience. Your past analysis experience certainly includes the analysis of the real numbers. Recall, the axiom of completeness of the real numbers states that every set of real numbers with an upper bound has a least upper bound. Okay, first off, that means that the real numbers are a complete ordered field. Standard definition of the real numbers, complete ordered fields. The field part is the algebraic part, multiplication and addition, and their interactions and the existence of inverses and so forth, the usual algebraic things. The order part deals with a greater than, less than. On the real numbers, there's an idea of one real number being greater than another real number. And when you hear order, that's the idea behind an ordering. Now, we're not going to have an ordering in our settings. So we're going to have to do something different from this kind of idea of axiom of completeness, because this idea, every set of real numbers with an upper bound has a least upper bound. So the upper and the least upper, and the ordering is all over the place there. So we're going to have to come up with a concept of completeness that doesn't involve this greater than, less than idea. So this idea of completeness, really informally, just between you and me, means that the space is a continuum. There's no holes in it. The rational numbers violate the axiom of completeness. Yeah, the rational numbers got a bunch of holes in them. They got holes in them everywhere there's an irrational number. So the idea of completeness is an idea of a continuum, really. And of course, this is vital in analysis because we want to take limits. And I need limits to exist when they, quote unquote, ought to exist. A limit of a sequence ought to exist, it turns out, when it's a Koshi sequence. So more of that shortly. But the completeness idea is an idea of a continuum. And so it's an essential idea to talk about limits and all that analysis stuff like continuity and derivatives, for that matter, in Calculus 1. Well, we need a formal definition, something better than this no holes in the space, the idea of a continuum. What's that mean? If we don't have an ordering, in the absence of an ordering, and you know, that's the situation with the complex numbers. There is no greater than, less than on the complex numbers. See my complex analysis notes for proof that there is no greater than, less than. That term ordering is used in set theory in a different way. So we're not talking about well orderings, that idea from set theory. This is the greater than, less than idea of an ordering that you're used to on the real numbers. So how do you talk about completeness for the complex numbers if you can't do this upper bound, least upper bound stuff? We need another approach to completeness, even in the complex setting. Quick footnote, you go through a standard complex analysis class, and completeness is dealt with based on the completeness of the real numbers. So that's a common way to address completeness there. That won't work everywhere. It won't work in the spaces we're in, for example. So we're going to take a different approach to completeness, inspired by the fact that in the real numbers, a sequence is Koshi if and only if it's convergent in the real numbers. That's not true in other places. It's not true in the rational numbers. The rational numbers form a field. They form an ordered field, but they don't form a complete ordered field. And I can find a sequence of rational numbers that's Koshi, but doesn't converge to a rational number because it converges to an irrational number. But this idea that in the real numbers, convergent, if and only if Koshi, we're going to use that to get to an idea of completeness in our spaces. We're in normed linear spaces. If we got norms, we can talk about Koshi sequences, and we can talk about convergent sequences. So that'll be the approach. Final comment from your past experience. In the reals, Koshi sequences converging is equivalent to the axiom of completeness. That is, if we assume that Koshi sequences converge, then we can show that sets with upper bounds have least upper bounds. We can show the axiom of completeness can be replaced with an axiom that Koshi sequences always converge. The fact that convergent sequences are Koshi, that implication is real easy. It's just the triangle inequality. We'll actually do this down below. Triangle inequality will show that convergent sequences are Koshi. It's the converse of that. Koshi sequences are convergent in the real number setting. That's the tricky part. All right. So maybe a quick historical comment. Who knew this first? I mean, who approached the definition of the real numbers like this as a complete ordered field? It was Dedekind. Dedekind in the 1850-something deals with Dedekind cuts, they're called today. And this was equivalent to the axiom of completeness. How about Koshi himself? His name's all over this stuff. Did Koshi know about the axiom of completeness? Well, Koshi, you can read from his original works, he assumed that Koshi sequences converge. So by assuming Koshi sequences converge, though he never explicitly stated so, but you can tell from his work that he was assuming that to be the case. Koshi himself was assuming an axiom of completeness, though not in a clean axiomatic way like Dedekind did. So funny bunch of trivia. What the real numbers really are, a complete ordered field. Axiomatically, that's an idea that dates from the 1850s. So surprisingly new, considering people have been thinking about continuums and the real line for a long time. Euclidean geometry involves a lot of properties of lines. But we will mimic this idea that in the real numbers, completeness is equivalent to Koshi sequences converging, and we'll actually take that as our definition of completeness in a normed linear space. So we need a few more definitions. A sequence x sub n in a normed linear space is Koshi if, given any epsilon greater than 0, there's a natural number, capital N, such that for all indices m and n greater than or equal to capital N, we have the norm of x sub m minus x sub n less than delta. Okay, so usual definition of Koshi. Remember, we have a metric here. The distance from x sub n to x sub m, that metric is induced by this norm. In fact, this is the distance from x to n to x sub n to x sub m. The norm of the difference is the metric, the distance between those two. So very much a senior level analysis concept involving Koshi sequences. Think of it as for all epsilon greater than 0, eventually there exists a capital N. Terms are close together in this sense. So there's an informal way to think of Koshi. The idea is these kind of sequences, just between you and me, these kind of sequences, Koshi sequences, they want to converge. And they will converge if you're in a complete space, because that's the definition of completeness that we're taking. A normed linear space is complete if every Koshi sequence converges. A complete normed linear space is called a Banach space. All right, so a bunch of stuff happened in the last 4 lines of this page of notes. Koshi standard definition, and taking as the definition of completeness that a Koshi sequence must be a convergent sequence. That's what completeness is in a normed linear space. We could have approached completeness of the complex numbers in a similar way in terms of Koshi sequences. And we've put a name on complete normed linear spaces. We've called them Banach spaces. This is a class about Banach spaces and Hilbert spaces. Banach spaces are complete normed linear spaces. Hilbert spaces are complete inner product spaces. In a Banach space, you can measure distance. In a Hilbert space, there's an inner product like dot product. So in a Hilbert space, you can measure angles. And that inner product will induce a norm, which in turn induces a metric. So there's more structure in a Hilbert space than there is in a Banach space. In Banach spaces, you can measure distances. Informally put, in a Hilbert space, you can measure distances and angles between vectors. And remember, the elements of normed linear spaces they're vectors. These are vector spaces. Banach spaces are vector spaces as well. They're complete vector spaces, which are normed. Some properties of normed linear spaces, really some properties of Koshi sequences in normed linear spaces. So 4 properties of Koshi sequences in normed linear spaces. See, I don't think we addressed the completeness in this particular statement, but completeness is going to play a giant role in what follows. Okay, so let's go through proof of proposition 2.9. First claim, as mentioned earlier, a convergent sequence is Koshi. All right, I promised you this wouldn't take anything more than the triangle inequality, and here's the proof. Take a convergent sequence, x sub n, say it converges to x. So x sub n converges to x. We have the definition of the limit of a sequence from previous sections. That means there exists a capital N, a natural number, such that for all indices, lowercase n greater than or equal to capital N, the norm of the limit value x and the terms in the sequence x sub n, satisfying this condition, can be made small. Let's choose small to be epsilon over 2 for a given epsilon. Take m and n both to be greater than or equal to capital N. Then the norm of x sub m minus x sub n, let's add and subtract x itself in there. So knowing this x exists, very much using the hypothesis that we have a convergent series. So we'll add and subtract x. We're able to put our finger on that value because we have a convergent sequence. Triangle inequality is promised. Break that up into the norm of the difference of the first 2 plus the norm of the difference of the second 2, pick up an inequality. Both of these are of this form. The indices m and n are both greater than capital N, so the epsilon over 2 bound holds. We pick up an epsilon over 2 plus epsilon over 2 equals epsilon. Probably should have started this with let epsilon be greater than 0, arbitrary real number as usual. But we've shown for any epsilon, x sub n minus x sub m in norm is less than epsilon. For m and n sufficiently large is given here. That's the definition of Koshi. So convergent sequences are Koshi. No surprise there. The converse of that, it becomes a more complicated story. More complicated story in senior level real analysis. And here it's related to the definition of completeness. Part B claims a Koshi sequence is bounded. That is, there exists some k such that the norm of x sub n is less than k for all n, a natural number. So suppose we have a Koshi sequence. We want to find this bound k. Then there exists a natural number n such that when the indices n and m are sufficiently large, is given, we have the norm of x sub n minus x sub m less than epsilon. Let's take epsilon equal to 1. This holds for all epsilon. We're choosing a specific epsilon. We're choosing 1. We're just trying to get a bound on these terms. So take epsilon to equal 1. There exists such a capital N. All right, if we take index n, lowercase n, to equal capital N, as introduced above, then we have x sub capital N minus x sub m, and norm is less than epsilon, that is 1. and this holds for all m greater than or equal to capital N. So eventually, all the terms in the sequence are within one of this x sub capital N, the x sub capital N being guaranteed up here by the definition of Koshi. So by the triangle inequality, really the backwards triangle inequality, I've never heard it called that before, but this book called attention to the backwards triangle inequality a few sections ago when we were first introduced to norms. We can get a bound here, something of the form, this is greater than the difference of the norms. We'd want to take the difference of the norms, norm of x sub m minus norm of x sub capital N. We get that as something less than the norm of the difference. Take that minus norm of x sub n to the other side, and it produces this equation. So small steps of algebra skipped, but we've got x sub m less than x sub m norm of less than x sub capital N norm of plus 1. And this holds for all m greater than or equal to capital N. Capital N is some natural number that we picked based on the fact that epsilon equals 1. And we've got a bound on all of these vectors, x sub m, when the index m is at least the size of capital N. So that's an infinite number of vectors that are bounded in norm by this constant, the norm of x sub capital N plus 1. So we got an infinite number of the vectors bound. We've got all but the first, n minus 1, capital N minus 1 vectors, and that's the ones that don't fall under this inequality. x1, x2 through x sub capital N minus 1, they could potentially be bigger than this bound. But beyond x sub capital N, all vectors have this bound on their norm. So if we pick the maximum of the first capital N minus 1 vector norms, and then this other bound, that'll be a bound that works for all vectors. That is, for all n, a natural number, the norm of x sub n is less than or equal to k, where k is chosen as given here. So we got ourselves a bounded sequence as claimed. So Koshi sequences are bounded. Koshi sequences are convergent. Convergent sequences are Koshi in part A. Part C says all subsequences of a Koshi sequence are Koshi. Okay, that's not in the least bit surprising. Let's get the math correct on this little argument, though. It's a little subtle with the subscripts. Let x sub n sub k be a subsequence of a Koshi sequence x sub n. Since x sub n is Koshi, then by the very definition of Koshi, for all epsilon greater than 0, there exists a capital N, such that for indices m and n greater than or equal to capital N, the norm of the difference is less than epsilon. All right, definition of Koshi. We want to show subsequences satisfy that as well. So take any k and l, these will be related to the subsequence. For any k and l greater than or equal to n, we have n sub k is greater than or equal to k, and n sub l is greater than or equal to l. We're making a claim here that n sub k is greater than or equal to k, which might not stand out to you as an easy result, but think what these symbols represent. K is a position in the original sequence. It's the kth position in the original sequence. N sub k is the kth position in the subsequence. So if the subsequence and the sequence itself are the same, think of creating the subsequence by thumping out a bunch of terms in the sequence. Then when you create the subsequence, the first term in the subsequence will be at least the first term in the original sequence. You might have removed the first term from the original sequence. If you did, all the subsequent terms are going to appear in positions further out the natural numbers than their original positions. So that's what this means. N sub k is greater than or equal to k. The position of a term in the subsequence is further out than that entry was in the original sequence. So if we take any k and L greater than or equal to n, then the n sub k will be greater than or equal to capital N, the n sub L will be greater than or equal to capital N, going through the intermediary k's and L's. And so if you look at the norm of x sub n sub k and x sub n sub L, that should read the norm of that difference, that's less than epsilon, because the indices are sufficiently large for this term to hold. So subsequences of Koshi sequences are Koshi, as claimed. Not a surprise. If x sub n is Koshi and some subsequence converges to x, then x sub n converges to x. All right. Not a property of regular old sequences. A sequence can have a subsequence that converges, but the original sequence not converge. Consider the sequence 1, 0, 1, 0, 1, 0, that diverges. But it's got a convergent subsequence, a subsequence of all zeros, or the subsequence of all ones. So sequences can have convergent subsequences, but not themselves be convergent, but not Koshi sequences. That's the claim here. If we have a Koshi sequence and some subsequence converges to x, say, then the original Koshi sequence also converges to x. The proof: let x sub n be Koshi and epsilon be greater than 0. Then there exists a natural number n such that for all values of the index lowercase n, at least as big as capital N, we have x sub n minus x sub m less than epsilon over 2. Another little typo there. It should read all m and n greater than or equal to capital N. We have this behavior, definition of Koshi. We've taken that less than small number to be epsilon over 2 for the given epsilon, but that can be done as well. Let x sub n sub k be a subsequence of this sequence that converges to x. So that's what we're hypothesizing. We want to show that the original sequence also converges to x. Well, subsequence x sub n sub k converges to x means there exists a capital J, a natural number. Without loss of generality, we can take capital J to be big. I mean, if this following property holds for small j values, and it also holds for big J values. So without loss of generality, choose this capital J to be greater than or equal to the capital N introduced earlier. Talking about convergence of the subsequence such that for all k indices sufficiently large, greater than or equal to capital J, we have x sub n sub k minus x less than epsilon over 2. Definition of convergent sequence. Well, definition of convergent subsequence, I got to talk about the k's in the x sub n sub k. The k's reflect positions in the subsequence. So you go sufficiently far out the subsequence, you get close to this limit point x. I want close to be epsilon over 2. All right, this holds for all k greater than or equal to capital J. In particular, it holds for k equals capital J itself. That is, x sub n sub capital J minus x is less than epsilon over 2. This inequality with k equals j. We did this so we can put our hands on some specific number. When I have a convergent sequence, I've got the limit value I can put my hands on. Here, we've got a convergent subsequence, but we've also got a Koshi sequence that we started with. And the property of Koshiness doesn't let you really put your hands on a fixed term so much. So that's the reason we're choosing this particular x sub n sub capital J. So if we choose index n to be greater than or equal to j, and therefore greater than or equal to n, that's why we made this choice up here, then we have the following. The norm of x sub n minus x, the distance from x sub n to x, what are we trying to show? The original sequence converges to x. So we're trying to show this is less than epsilon. So it looks like it's going to work. All right, we did something like this above. Let's add and subtract that term we got our hands on, x sub n sub capital J. Subtract it, add it, so we haven't changed anything. Apply the triangle inequality. Each of these are less than epsilon over 2. The second one is less than epsilon over 2 because that's what it says right there. The first one is less than epsilon over 2 by the Koshiness property. We got this going on. Provided the indices are at least capital N, lowercase n is at least capital N, and x sub n sub j is also at least capital N. Remember, we have x sub n sub j greater than or equal to capital J, and in turn, greater than or equal to n. So these indices are sufficiently large that that norm is less than epsilon over 2. Using the Koshiness here and the convergence here of the subsequence. Epsilon over 2 plus epsilon over 2 equals epsilon, and that's exactly what we wanted to show, that the original sequence x sub n converges to x as well. All right, back to the notes. That was the last part of that one. All right, this previous result still doesn't allow us to test a sequence for Koshiness. We got the definition. It gives us properties of Cauchy sequences. The next definition, as we'll show, gives a technique for testing a sequence for Cauchiness, my term there, just beyond something in addition to the definition, as we'll see. A sequence, x sub n, is said to be a fast Cauchy sequence if the norm of x sub n plus 1 minus x sub n is less than 1/2 to the n. The exponent on the 1/2 related to the smaller of those two indices. So what we're doing is looking at the norm of the difference of consecutive terms in a sequence. Cauchiness dealt with terms, pairs of terms. They didn't have to be consecutive sequences. It dealt with the norm of x sub n minus x sub n, where m and n were sufficiently large. Here, we can certainly make this small by making n large, but this just deals with the difference of consecutive terms. Might catch your eye that if we were to sum this up on the right-hand side over all natural numbers, we'd have ourselves a geometric series. And I don't know much about the convergence of series, but I know the convergence of geometric series. And that'll pop up in a discussion about series here shortly. All right, so there's a definition of fast Cauchy, relatively uninspired, but we'll have some results that'll make it more inspiring. Quick comment, if you've taken real analysis 1, probably real analysis 2 is where we cover this stuff. This sequence of 1/2 to the n for all natural numbers n, this was a requirement, used in this definition of fast Cauchy sequence, could be replaced with any positive term sequence a sub n, which is convergent to 0. In Royden's real analysis book, Royden and Fitzpatrick these days, they picked up a co-author some years ago. Sequence x sub n is said to be rapidly Cauchy if there's a series of positive numbers, epsilon sub n, that is summable, a summable series of epsilon sub n's, for which the norm of x sub n plus 1 minus x sub n is less than or equal to epsilon sub n squared. So that's fairly similar to what we've done here, called rapidly Cauchy. This is addressed in the graduate real analysis class in the setting of LP spaces. In fact, in showing the LP spaces are complete, so it was not surprising that it pops up in this conversation. More to follow on what the LP spaces are, but one thing the LP spaces are, they're Banach spaces, and we're talking about Banach spaces. We're trying to talk about complete normed linear spaces, so there's certainly a connection here. Anyhow, you might see this somewhat different definition, a kind of promislo to use different verbiage, similar but different verbiage, fast Cauchy sequence versus a rapidly Cauchy sequence. But we'll stick to Promislo's definition, but you may see this in other settings in your past or in your future. Proposition 210 says, in a normed linear space, a fast Cauchy sequence is Cauchy. Okay, so that gives us a way maybe to recognize that a sequence is Koshi. If we can show it's fast Koshi, then it's a Koshi sequence. Any Koshi sequence contains a fast Koshi subsequence. All right, so there doesn't seem to be an equivalence between Koshi and fast Koshi, but certain implications. Fast Koshi implies Koshi, and Koshi sequences have fast Koshi subsequences. Let's go ahead and make a little observation here, lumping together the previous result we proved along with this one. We'll do the proof of this one as well. It follows, it says that a normed linear space is complete if all fast Koshi sequences converge. All right, why is that? Because to show completeness, we would show all Koshi sequences converge. Well, we know from here that any Koshi sequence contains a fast Koshi subsequence. So if we showed that fast Koshi subsequences converge, we would be then establishing that any Koshi sequence has a convergent subsequence. That convergent subsequence happens to be fast Koshi by proposition 2.10 part B. We would be establishing that a Koshi sequence has a convergent subsequence if we can establish this thing in blue. Hey, but wait, if a Koshi sequence has a convergent subsequence, then the Koshi sequence itself converges. That's the last thing we showed. So pasting together those two observations, to show completeness, it's sufficient to show that fast Koshi sequences converge. And we'll establish completeness by showing that. All right, let's go through proof of proposition 2.10. First, a fast Koshi sequence is Koshi. Okay, part A. Let x sub n be a fast Koshi sequence, and let epsilon be greater than 0. We want to show regular old Koshiness. That is, we want to show the norm of x sub n minus x sub m is less than epsilon. So it looks like it's going to work. Choose capital N, a natural number, such that 1 divided by 2 to the capital N minus 1 is less than epsilon. Hey, 1/2 raised to powers can be made arbitrarily small and positive. So it can be made less than epsilon for any given epsilon. So choose capital N such that 1/2 to the capital N minus 1 power is that small, less than a given epsilon. For n and m greater than or equal to capital N, we have the following. The norm of x sub n minus x sub m, notice we've assumed n is greater than m. In this case, one of them's bigger without loss of generality. Suppose it's n. Then what we would get would be x sub n minus x sub m. Say we take the x sub m and add and subtract x sub m plus 1, and add and subtract x sub m plus 2, and add and subtract and so forth, up through adding and subtracting x sub n minus 1. That's why we wanted that ordering on there. We're putting in a bunch of zeros, but those zeros correspond to terms between x sub m and x sub n. Also, it looks like we've introduced maybe a negative sign here. And actually, that's an equality because all these cancel out. So I should have an equality there. Finite sum of vectors. Let's use a triangle inequality on it. All right, so we're going to break this up over the pairs. We've got an x sub m minus x sub m plus 1, plus x sub m plus 1 minus x sub m plus 2. Break this up using the triangle inequality. It's written it with the larger index on the left. I mean, it doesn't matter. Of course, that'll absorb negative signs. And this, with the triangle inequality, is less than or equal to a sum from k equals m to n minus 1 of this. We want to look at consecutive terms because we've made an assumption of fast Koshi. How big is the norm of x sub k plus 1 minus x sub k? It's less than or equal to 1 over 2 to the k. The power of the exponent here was the same as the smaller of the two indices, if you'll look at the definition. So we get this bound. Sum from k equals m to n minus 1, 1 over 2 to the k. You wouldn't argue that that's not less than sum from k equals m to infinity of 1 over 2 to the k. So we just threw in an infinite number of terms at the end. They're little terms. Why would you do that? Well, that's a geometric series, and I know how to sum that. And I probably know how to sum this as well, but we're just trying to get a bound. So geometric series, first term is 1 over 2 to the m. The ratio is 1/2. So there's the sum of that series. Simplifies to 1 over 2 to the m minus 1. M was greater than or equal to capital N. So m minus 1 is greater than or equal to capital N minus 1. We've gone to the denominator and made these exponents. So this inequality justifies this inequality. So we've got the norm of the difference, x sub n and x sub n, less than or equal to 1 over 2 to the capital N minus 1. And we had chosen capital N such that that would be less than epsilon. So there's the for all n and m greater than or equal to capital N, norm of the difference is less than epsilon. It's a Koshi sequence. So fast Koshi sequences are Koshi sequences. Next, any Koshi sequence contains a fast Koshi subsequence. So now a result about subsequences. Okay, take yourself a Koshi sequence, x sub n. Choose n sub 1, a natural number, such that for all m and n greater than or equal to capital N sub 1, we have x sub m minus x sub n less than epsilon. Actually, let's take epsilon equal to 1/2. Hypothesis of Koshi, for any epsilon greater than 0, like epsilon equals 1/2, there exists such a capital N sub 1. Do it again. Pick an n sub 2, such that n sub 2 is strictly greater than n sub 1. We can make n sub 2 large if you like. For all m and n greater than or equal to n sub 2, we have the norm of x sub m minus x sub n less than 1/2 squared. Think of that as epsilon, and so forth. So do that for these powers of 1/2. Inductively choose capital N sub k, strictly greater than capital N sub k minus 1, such that for all m and n greater than or equal to that chosen capital N sub k, we have the norm of x sub m minus x sub n less than this epsilon, 1/2 to the k power. So done in terms of the index k. Then consider the subsequence capital x sub capital N sub k. Consider this subsequence. Well, we made this subsequence such that x sub capital N sub k plus 1 minus x sub capital N sub k is less than or equal to 1/2 to the k. Right? Where k is the ultimate index on this term with a smaller index. That is fast Koshi. And in fact, this is kind of constructive proof in some sense. When you were choosing these n sub 1s, we didn't have a clean way to choose those. We know the existence of them. But I'd half-heartedly at least argue this as a constructive proof. We've constructed a subsequence of a Koshi sequence, which is fast Koshi because of this relationship here. Back to the notes. All right, we had an observation about how to use that, and we'll see that when we address completeness on down the road. Okay, let's shift gears a little bitty bit from sequences to series. In a normed linear space, the series, sum from I equals 1 to infinity of x sub I, is said to converge to x, denoted sum from I equals 1 to infinity of x sub I equals x, if the sequence of partial sums, that is S sub n, defined to be the sum of the first n terms in that series, converges to x. As usual, we're defining the limit of a series in terms of the limit of the sequence of partial sums, just like in calculus 2. Here's what those partial sums are, and we consider the sequence of partial sums. A property relating norms to series if x is the sum of this series, x sub i's. So this series has a limit. The sum of the series exists. Then the norm of x is less than or equal to the sum of the norms of the x sub i's. Bet you it looks a lot like a triangle inequality, right? We're taking a norm of a sum and relating it to a sum of norms. Only thing is, and these ain't sums, they're series. Okay, so the proof is based on the triangle inequality and limits. So I like this one because it's very short. Okay, we had continuity of the norm a few sections back, theorem 2.3 part C, told us you can take limits in and out of norms. That's what continuity means in general. So we have from that property and the triangle inequality the following. X is the limit of the sequence of partial sums. So x equals this limit, the norm of x equals the norm of the limit. We can bring the limit outside the norm, that equality, that's your theorem 2.3 part C, there's continuity of the norm. Limit came outside of the norm. S sub n was a finite sum. The triangle inequality only reliably applies to finite sums. S sub n was the sum from I equals 1 to n of x sub I, the sum of the first n terms of that series. We still got the limit thing out there. You can apply the triangle inequality to finite sums. That's the reason we've done this, the way we've done this. Triangle inequality tells you the norm of the sum is less than or equal to the sum of the norms. Triangle inequality and induction, arguably. What do you get when you take the limit as n approaches infinity of a sum from I equals 1 to n, blah, blah, blah? Well, that is by definition, that's the series, sum from I equals 1 to infinity of the norms of the x sub i's. Now, about this series, that series is a series of real numbers. Well, not just any real numbers. This is a series of non-negative real numbers, commonly called a positive term series, even though it could have terms that are zero as well. But this is a positive term series. Does it converge? Well, not necessarily. It could diverge, but if it diverges as a positive term series, it would diverge to infinity. In which case, we've trivially got the norm of x is less than or equal to infinity. Legitimate to write infinity here because whenever you see the infinity symbol, you know we're dealing with limits in some sense. There it is explicitly right there. Limits can be infinite. Numbers are not infinite, but limits can be infinite. So we didn't put any constraints on the convergence of this. It could well be that this diverges to infinity, in which case this is a fairly uninteresting observation, but it's still true. Back to the notes. Let's talk about that series of norms. A series, sum from I equals 1 to infinity of x sub I, is said to be absolutely convergent if the series of norms of the x sub i's, sum from I equals 1 to infinity of the norm of x sub I, converges. All right, you dealt with absolute convergence in calculus 2 and senior level analysis, probably a bit more. The beauty of this little statement here is that's a positive term series. By the way, after calculus 2, you know a lot of stuff about positive term series. You can test them for convergence or divergence. You've got ratio tests and root tests and integral tests. All those things were tests for positive term series. And remember, a positive term series has no negative terms. Seems they ought to call them non-negative term series, but positive term series is the common terminology. So anyhow, we know some things about this because that's just a series of real numbers. If it doesn't converge, we do know it diverges to infinity because it's a positive term series, and that's how positive term series of real numbers behave. All right, the following result gives another way to establish completeness. It says a norm linear space X is complete if and only if every absolutely convergent series is convergent. Okay, you've seen in the setting of the real numbers some convergent series that are not absolutely convergent. They're called conditionally convergent. An example is the alternating harmonic series. 1 minus a half plus a third minus a fourth plus a fifth and so forth. That's a convergent series of real numbers by the alternating series test. And if you take the absolute values, you get the harmonic series, which diverges. So convergent doesn't imply absolutely convergent. If you remember your calculus 2 really well, or your analysis, senior level analysis moderately well, you know in the setting of the real numbers, absolutely convergent series of real numbers are also convergent. Yeah, that's because the real numbers are complete, we could say in light of this result. But we're giving a classification of completeness in terms of convergence of absolutely convergent series. So let's look at a proof of that. Normed linear space X is complete if and only if every absolutely convergent series is convergent. So suppose X is complete. Consider this sequence X sub I, which yields an absolutely convergent series, right? These are the terms of the series, in other words. So we're taking a complete space, we're assuming completeness, and considering an absolutely convergent series, we want to show that series, in fact, is convergent, assuming it's absolutely convergent, and that the space is complete. Okay, the sum from I equals 1 to infinity of the norm of the X sub i's must be finite. That's what absolutely convergent series means. So let epsilon be greater than 0. For index n, sufficiently large, the tail of that convergent series must be small. The sum from I equals capital N to infinity of the norm of X sub I must be less than epsilon. That's just from the very definition of this sequence being convergent. We'd take partial sums and make them close to the limiting value. And if you look at the limiting value minus the partial sum up through S sub capital N minus 1, say, you get this as the tail. So this is the difference between a partial sum and the entire series. If it's convergent and we make the index sufficiently large, then the distance between the limit value and the partial sums must be small, less than epsilon. It's the definition of limit, actually. So if we take n and m sufficiently large, then we have for the partial sums, S sub n minus S sub m, take an n greater than m here, one of them's greater, say it's n. This is the sum of the first n terms. This is the sum of the first m terms. So when we take a difference of those, we lose the first m terms from here when we subtract those away. And we're left with a sum from I equals m plus 1 to n, right? The next term that's not in this partial sum up to the last term here. So we get a sum from I equals m plus 1 to n, X sub I. That's what the difference of two partial sums are. We're taking norms, so we got a norm on that. It's a finite sum. Triangle inequality applies to finite sums. So we can say less than or equal to sum of the norms. Tell you what, I know if we sum from I equals m plus 1 to n, these norms, that's certainly less than or equal to the sum from I equals m plus 1 to infinity of the norms. So we've taken this tail of a series, we've added in an infinite number of non-negative terms. And we made the index m sufficiently large so that we would get the sum here to be less than epsilon. So m is sufficiently large so that this sum, notice it looks almost exactly like this. Starting value is different, but we're good. This will be less than epsilon. So we've shown that the sequence, be very careful with my words because we're talking sequences and series here. The sequence of partial sums is Koshi. For all m and n greater than capital N, norm of the difference is less than epsilon. Yeah, that sequence of partial sums is a Koshi sequence. What were we assuming here? We're assuming completeness. What's the definition of completeness? Koshi sequences converge. It is in here in norm linear spaces. So by showing S sub I as a Cauchy sequence, then we know S sub I converges because we've hypothesized that the normed linear space is complete, and that means Cauchy sequences converge. So this series S sub I converges. That is, the absolutely convergent series, sum of the X sub I's, is in fact convergent. The S sub I's were partial sums for the original sequence. Right? We took sums of the X sub I's, not sums of the norms of the X sub I's. So we've got convergence then of the associated series. This is the series associated with it. So absolutely convergent implies regular or convergent in a complete normed linear space. All right. You might want to be aware of where we use completeness, right? It was right there. Without the completeness, we get stuck. So the completeness played a big role, and it played it right there. This result you show in senior level analysis, and possibly even calculus too. Absolutely convergent series of real numbers are convergent. Yeah, because the real numbers are complete. The converse would be, whoops, let me go back. Converse would be if every absolutely convergent series is convergent in a norm linear space, then the norm linear space is complete. So we'll hypothesize every absolutely convergent series is convergent, and we'll try to show completeness. So now suppose every absolutely convergent series is convergent. We want to show completeness. That means we want to show every Cauchy sequence converges. Well, we're going to take a little detour before we do that. The bottom of the slide will deal with Cauchy sequences. Let's talk fast Cauchy sequences in the short term. Let X sub n be a fast Cauchy sequence. The series, sum from I equals 1 to infinity, X sub I plus 1 minus X sub I. We're going to claim this is absolutely convergent. Look at the sum, X sub I plus 1 minus X sub I, n norms are the series. This is less than or equal to a sum from I equals 1 to infinity of 1/2 to the I. Power on the 1/2 is the same as this little index here. Yeah, we said suppose it's a fast Cauchy sequence, so it satisfies these conditions. That's the definition of a fast Cauchy sequence. Oh, this is a geometric series. Geometric series, first term is a half, ratio is a half, converges to 1. So this fast Cauchy sequence is absolutely convergent. We're hypothesizing that every absolutely convergent series is also convergent. So it must be that this series is also convergent. That's the hypothesis we're making. If absolutely convergent, then convergent. Hypotheses here. And say this series converges to X. That means the partial sums for that series, of course, take a partial sum of this, we'd add up, say, from I equals 1 to n. What we've got here is really a little telescoping situation where we'll be left by summing from I equals 1 to n. We'll be left with the last term minus the first term, isn't it? We stop at index n, we'll be left with X sub n plus 1 minus X sub 1. All the intermediate terms canceling out. It's telescoping. So we get the partial sum S sub n for this series is X sub n plus 1 minus X sub 1. We know that the series converges, say, to some number X, that is the S sub n's converge to X. So this stuff here as n approaches infinity converges to X. Something we can rewrite as X sub n plus 1 converges to X plus X sub 1, getting the indices all on one side of the equation, just doing a little bit rearranging there. So we get this sequence X sub n plus 1 to converge to X plus X sub 1. So let's tweak that index just a little bitty bit. That's equivalent to saying X sub n converges to X plus X sub 1. Think of this as a limit as n approaches infinity. Well, that's a limit as n approaches infinity as well. N plus 1, n, no difference when we take limits as n approaches infinity. So we've got the sequence converging to, this sequence converging to x plus x sub 1. The fast Koshi sequence is convergent, when that was hypotheses. Since x sub n is an arbitrary fast Koshi sequence, this shows that fast Koshi sequences are convergent. See, did I get that correct? I think I misstated something. This sequence x sub n is a, here's where I should point, this sequence is a fast Koshi sequence, excuse me, and we've shown that that fast Koshi sequence converges. Sorry, that wasn't hypotheses. That's been established in the argument here. Fast Koshi sequences are convergent under these hypotheses. X sub n is an arbitrary fast Koshi sequence, so every fast Koshi sequence in X is convergent. But that ain't what we're trying to show. We're trying to show completeness. We want to show that Koshi sequences converge, because that's what completeness is. We've shown that fast Koshi sequences converge. Well, that's close enough. We were talking about this a while ago. So let x sub n prime be any Koshi sequence in this space. We're going to show it converges. By proposition 2.10.b, we know that x sub n prime, being a Koshi sequence, has a fast Koshi subsequence. This was a comment we made after proposition 2.10. So this Koshi sequence has a fast Koshi subsequence. Well, we just showed here every fast Koshi sequence in X is convergent. Well, then this is a fast Koshi sequence in X, so this is convergent. So x sub n sub prime is a Koshi sequence with a subsequence which converges. Proposition 2.9d says if you got a Koshi sequence with a subsequence it converges, then the Koshi sequence itself converges. That's the thing we went back and talked about. So having a convergent subsequence, the original Koshi sequence, x sub n sub prime, must also converge in X. So what we've done, and starting right here, is taken a Koshi sequence and showed that it converges. If an arbitrary Koshi sequence converges, then every Koshi sequence in normed linear space X converges, and that's the very definition of completeness in our setting. So this gives an equivalence between completeness and behaviors of absolutely convergent series. And again, this is probably something you saw in senior level analysis. So that'll do for now. So we'll split this section into 2 videos and come back and finish the rest of it here in a little while. I'll see you then. Bye-bye.